Hello, good morning. Welcome to the course of Introduction to Artificial Intelligence. In the last lecture, we have studied the adversarial search and we have covered the topic or what is adversarial search, game theory, and we have also studied the min-max algorithm and the alpha-beta, the disadvantage of min-max algorithm and how to overcome with alpha-beta pruning algorithm. Now today we go more detail about the alpha-beta pruning algorithm. So we have to think about what are the bad cases and the good cases of the alpha-beta pruning. So if this is the slide I'm showing you was a bad case and the following one was a good, which I have not marked as yet. So let's say I'm the max and I order my notes as a 2, 3 and 4. If I order my notes as a 2, 3, 4, so after I explore 2, I will have to explore 3 because 3 will finally be better. And there is just no way I I can't explore 3, I have to explore 4 because 4 will be a better. Similarly, a children 2 will be a mean node and I have ordered them as a 6, 4, 2. So once I get the value of 6, I will have to explore 4 and will have to explore 2 because 2 will give me the finally correct answer. So this is my bad case scenario of the min max algorithm. So if my better children or best children are the most are the last, I will have to explore everything. So this is showing the example there will be no effect of alpha beta pruning. You will think about it after you done with the left subnodes. My alpha would be 2 and once I go down the first child of 3, so beta will be 7 and it is not going to be hell because your alpha is never going to be greater than beta. So I moved up and my max will become 3 and my max become 3, alpha become 3. But again my beta will be start from 8, then go 6 and then go 4. Will never able to, so the alpha will never able to greater than the beta, so it is no, or not equal to beta, therefore it will not able to prune anything. Okay, so now question, how should I order those nodes so that I can prune something? It is very easy question if you have understand this so far. So example of 3 subtrees, 2, 3, 4. How should I order them so the maximize the hope of pruning? The answer is very simple. If I order this 2, 3, 4 as a 4, 3, 2, I will get the best or the good case of the pruning. So I have to return here. So this should be my 4. Okay, there is some mistake. This should be a 4. This should be a 3. And this should be a 2. If I do this way, then I don't have to explore everything. I just have to explore this way. So once I bought my best part early on, I have bought the best bounce. And if I get the best bounce, my hope of pruning is increasing. Similarly, for the children of a 4, how should I order them so I get the best pruning? If you see, I have ordered here 6, 4, 2, 7, 5, 3 and 8, 6, 4. So now in 4 is my mean, then I have to order them as a 4, 6 and 8 to get again a best prune from the mean side. So I started with the mean first. So 4, 6 and 8 will be answer. So in this way, I will get the maximum pruning. Now here is a question that I'm going to answer in second slide. But I should have to start thinking. Suppose I give you the best pruning. Now you remember that min max search has b to the power n. Suppose in the times complexity. I give you the best ordering of the node to give a best pruning, what will be the times complexity in alpha beta pruning and how you will be compute it. So actually, let us ask the question first. This is the best pruning, what is happening, and the answer to that question. First, write a recurrence relation from the simplex min-max search from the depth first search in the factor of b, and if a depth as a m. So that we'll see in the next slide. So this is what we're talking about, the times complexity. So suppose in normally, if we are talking about a min max search algorithm, or we can talk about the bat first search algorithm. Let us say I define T of m be the times complexity of a search. So it is a root node under which I have tree of the uh, depth. So what would be recurrence relation of T of m for regular min max search in terms of T of m minus 1? So basically the relation will be look like T of m is equal to b times T of m minus 1 plus some constant. Now what is constant doing? It is just the maximum that sort of C, and it is not seeing maybe, then it is b. So it will be a b times T of m plus 1 plus b in the worst case. So this is T of m would be order of b to the power m when you solve by mathematically. So we will get T of uh, o or T of m of the order b raised to m in the normal case. Now we have to think about what will be the best case scenario in alpha beta pruning. So this is a hard question. Of course, can we write similar recurrence relation trying to represent T of m as a lower order of T of m minus 1 and T of m minus 2, etc. for alpha beta pruning? If alpha beta pruning is being done on the tree with the best order of the nodes, and the figure gives you hint for me to compute T of m, what do I absolutely have to compute the correct value of the first child? I have to compute the correct value of the first child, because only when I go to the good alpha, for example, assuming that minimum root is the maximum, this reverse if minimum root is a minimum, nothing change. Now that I have to compute the best value, and I simply have to prove that it is the best value. Now with this intuition, I can tell you what is going to be a best recurrence relation for T of m. I only have to evaluate one of their children, which would be a depth of m minus 2. So I get this as my recurrence relation of T of m minus 1 plus b minus 1 times T of m minus 2. So this is what I relation get plus some constant. So if I try to again realize solve this by geometric progression, I will get T of m will be the order of b raised to m by 2, which is the half of the min max algorithm. So this will give you a substantial improvement. So think about it and understand that how much alpha beta pruning gives the better time complexity comparatively min max algorithm when you do a perfect reordering of the nodes. Again, we have to consider the best case scenario while finding the times complexity. Now we go to the properties of alpha beta pruning. So pruning does not affect the final result. Prune only the suboptimal nodes. Prune away the provably suboptimal nodes. It is not making any approximation. It always get the optimal result. If I can search till very end, or even if not, whatever min max does, it does the same thing. It is the same result good to move ordering makes one level of the difference. So if you do the best ordering, you will get the best result in alpha beta pruning. So now you start thinking in back your mind, how can I order moves better, or we will come to that later on. But good move ordering improves the effectiveness of the pruning significantly, because in the worst case, no pruning will give me the b to the power m. In the best case, a lot of pruning can give me the b to the power m by 2. So I give you a minute, you are able to search till the depth 4, because your complexity is b to the power m. But with the good pruning algorithm, you can search to the depth of 8, and which will give the maximum effectiveness in your times complexity. So just by searching for more depth, you will have a better understanding what you will know the better move, because if we have a better understanding, then you get obviously we get the best move, better move, and you can look ahead far enough. And now I want to introduce one simple concept, and that concept is meta reasoning. What is meta reasoning? The meta reasoning is nothing but reasoning about reasoning. So whatever you hear, the word meta is just expanded like meta learning. Meta learning is learning about learning. So meta learning is actually very famous field of the research. It is one of the next big thing in the machine learning. So why it is called meta reasoning? Why it is reasoning about reasoning, and what it is doing in alpha beta pruning. So what alpha beta pruning is the doing, so we call it as a meta reasoning. So it is saying where should I expand, or where I should not expand, where should I go and try and figure out what is the best action, and where should I say this is not interesting and let me not go even more. So the process which gives out where to go, where not to go, is the thinking process, and the alpha beta pruning process. And that thinking process is deciding where to think, where to go, where to expand, and where not to expand. So this alpha beta pruning is a sort of urging all my subtrees and saying, you, a subtree looks promising to me, so I will go and explore this node. Or this subtree looks not fine to or promising to me, I will not go and not think about it. So therefore, it is a sort of doing one kind of meta reasoning. So that's why this meta reasoning is very important. Now again, we will give one more intuition behind this. So when you are thinking, your time is going, and when other person is thinking, the time is a good, and your goal is to think faster based on the remaining time, and the remaining time takes, and you have to take a move. Now you may have met some people who just keep thinking but do not really take any action, and that is also not an ideal case, because of course if you think more, you will they will probably take more optimal action. But optimal under what circumstances? Because you have to pay more time to get optimal action. So it is ideal, it is a good to give more time, it is good to do more thinking and do not and don't take an action. If we'll just uh, take some philosophical example. If all your life you are only thinking to find optimal solution and never execute it, you will never get the rewards. You will never achieve what is the goal that you want to achieve. Eventually, life will in life we have to think and act, and we are in given limited time to think, or we may decide to take more time to think, but then you have to pay the price of cost of the thinking further. And so the meta reasoning process typically say, thought about it enough, so I can be sure that I am deciding an optimal action at this point. But if I trade off between thinking of more and just taking action and moving forward at this point, I should say, let me take the action, not just continue thinking. The process is something like a meta reasoning. It is saying in the context, I should stop thinking and start acting. So even I am reasoning about how much do reason. So now, do you divide a time for your move equally, or do you spend more time earlier or less time later? So now we have a fixed amount of time and we have to give that time to each and every move. So what you will do, first you give more time to thinking and then act, and you give lesser time in the later stage. So or you will divide equal amount of time throughout the process in each move. Okay, so what you will do, the question, those are the questions that you have to grapple with when you design your game board. All those questions come into the preview of the meta reasoning. So the next question, how do I order my nodes such that I get the best alpha beta pruning? Of course, I don't know the value is until I go to the leaf of every time. So it is very hard. So what could I do? I have many children. I need to figure out which I will do explore first, explore first child to explore the later in the hope that will give me the best alpha beta pruning. Some kind. So for this we need some kind of heuristic function. We say higher value is better and figure out which node you want to explore first. And this is what we are going to come in. But even then, this is the evaluation function without any search whatsoever. Suppose I wanted to use a little bit of search to figure out you, which is better not to search, where remember, with every depth first search algorithm, it is associated with iterative deepening depth first search algorithm. Now with that hint, can you think of good node ordering mechanism? Yes, we can. The good node of ordering mechanism, we can use iterative deepening, which do its research to the first depth, go back, search to the second depth, go back, search to the third depth, and so on. Well, after it has done searching for the first depth, it has some idea of which are better children, so it can order them that way and search the second depth of association to the second depth. Hopefully it will do alpha beta pruning, so it will not be the bad. But then it will have more information and it can learn that information use it a reorder all the children searcher to the depth, third depth, and so forth and so on. So this is one mechanism where people use iterative algorithm for better pruning. Now we are going to study one more a new algorithm, that is cutoff alpha beta pruning, or we can say min max cutoff algorithm. So what exactly we are going to do? We cannot search the entire leaf. We have to stop in the middle of the depth. So rather searching of 8 depth, or I will search till b to the power of 4, that is till the fourth depth. But we have to stop in the middle, and this algorithm is called the min max with cutoff or alpha beta pruning cutoff algorithm. So what we are going to do, the replacement, that terminal is replaced by the cutoff and utility is replaced by the evaluation function. And it is very important things you have to study the evaluation function here. So depending upon how much you can see, even if you play the chess or any game, what you do, you think about, if I move my pawn, the opponent will move the bishop, then I will move something this, and the opponent will move this, and we just think, but we think up to a certain limit. then you stop. And this is how it looks like. When I moved a pawn, well, what if I moved my king, and then how does it look like? So with every move you think a little bit how the future is going to look like, and you do not go to the very end of the game to analyze the entire game and all the possibility of you and your opponent. So you make a decision after reaching a certain limit. So this will give a intuition of alpha, cutoff alpha beta pruning, that you will prune, or sorry, you will do the cutoff here, and you just do a search till here, and then you decide which is the best move, and later after this you go ahead. So our point is, well, we are not going to able to do very end of the depth. We are just going to cut off it in the middle, and you will have to do it because we just cannot get to the end too, because you know what is the reason behind that, the time complexity. But of course, now the question, what path has right? The question that how much cutoff I have to decide. Eventually, we don't know nothing about it, so we start doing some kind of randomness. The intuition is going to be a sorter, and the answer is going to be what has really given. We will allow our search to stop in the middle, and we will think this is lives, but we do not know who wins and who loses. So we will somehow evaluate whose position is stronger, me or my opponent, in the leaf of this artificial leaf somewhere. So I will give you a best example of this. Okay, so this is what we will call, we will find the evaluation function in the middle of the board position, and that thing at this point your computer is much better than your opponent, then you will get the win according to this. So we will call the evaluation function. For example, if I take tic-tac-toe games, of course this is a very simple example, you can even search till the very end, but suppose I stop in the middle and I wanted to predict who is going to be win, or whose position is stronger, and what may be a simple way to achieve this. So well, let us say I define the idea. I will count number of rows, columns, and diagonal in which the computer can win, and similar I will find the number of rows, column, and the diagonal in which opponent can win still, and I will take the difference of them, and that is I will call my evaluation function. So let's say this is the example. So can anyone tell me that suppose in the first case, if I have stopped somewhere here, what are the chances of winning X? So if you see, the chances of winning X is 1. I just, so this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So total there are 6 chances what way a computer can be in the first, according to this criteria. But we'll see now the way of opponent win. O. So O has a 1, 2, 3, and only 4 chances. So this has a 4. So by this middle of here, we can see the computer is stronger than the opponent. Now again, we'll take this one more example. We will count for the opponent. So you can see there is no any chance of opponent to win. We will, no, there is one chance. This is a one chance. Okay. Is there any another chance? No. Okay. So opponent have only one chance. But if you see the computer have 1, 2, 3, 4, total 4 chance. So you can see this is how you do cutoff, and you can find. So basically we will not just do this with our evaluation function will be the difference of this. So if the difference is positive, the computer will win. If the difference is negative, then the chance of opponent will, and if it is 0, both the chances of tie is higher. This is what we can conclude, and this is what our evaluation function. Again, this evaluation function is very simple. Okay. So the idea of number of those column and diagonal which decide minus the whatever this idea, it is nothing but just one evaluation function we can say. And now I told the computer that this is a good property and use this as the evaluation function, and this property will determine the evaluation function of that point, and I will use this, I will use that to back it up. Is it well formed? Setup now does make a sense. Just to repeat, this is actually important and the most important part of today's lecture. So I am doing min max search with alpha beta building, and I do cutoff and I stop somehow in the middle, and I cannot search further, and I do have the time. So what we have seen from the starting that I have just said, that I'm doing min max search with alpha beta building and with cutoff. This is what we have end up with the third algorithm. Hope this is clear to everyone. Now we move ahead. At that point, I have only partial board in position, and I have not reached till the end, and I will evaluate this partial board position. How would I evaluate it? I will come up with some property of the domain which say which whether this board position is my favor or the opponent favor, and how much that will be the value of the leaf, and I will pick it up. So at the top, I will be taking the action which maximize the utility function of the point of cutoff, and the utility function will define by me. But of course, it is very hard for me to define utility function for every state. For a game like TikTok, it might work. But let us say I am giving you a game like chess. How would you do it? So there is a traditional way to do, and there is some modern way. In modern way, the machine learning kind of concept will come in the picture. This is first time I have you. We are a little bit talk about the machine learning perspective over here. So if I have a game like chess, I will see how many queens do I have, how many pawns are near, how many queens the opposite have, how many pieces of total number of pieces does opponent have, how many total number of pieces do I have, how many bishop the opponent have, I have. This kind of extra so many features will be there, and I will defining them, and I will call these all as the features value. So where do those features come from? So these all features we invented. So this is very important to define the feature. For example, one feature will be a number of white queen minus number of the black queen. So that is what, as you've seen in the picture, F1 of S. So similar kind of, I'm defining 50 features, 100 features, and my goal is to define the partial, I mean the board configuration and for each board configuration, what will be my evaluation function. So my evaluation function will be W1 times of F1 of S, W2 times of F2 of S, and Wm times of Fm of S. Now the question comes, what is W1, W2, and Wm? So in the game like chess, every player has some good property. A queen has the best property. So if you have a more queen, you have a more chance of winning. But understand? So that's why we have to give the weight to each and every features value. And these weights, initially we do the random, we give the random weights, and later on as we move, we study, we understand that this feature has more importance and this feature is the less important, and we try to vary the value of the weights. And this is what the machine learning is doing. Again, we are not going to talk about the machine learning in detail, but this is how you get some function, and the machine learning will just try to optimize your function and try to adjust your way to give a maximum evolution function. So I have not defined all the features, and now I need somehow to compute the weight. So we have, whenever I am setting where I have to learn something, so some data is that we got the machine learning. So I hope this is clear to you till here. Now if you have any doubts till here, you can ask me the doubt, and then I will move to the next topic.